Hello everyone, myself Dr. Radhika, working as Senior Assistant Professor in the Department of VJEC VJEC. In today's topic, we are going to see the transformer EMF equation, and we are also going to solve some numerical problems based on that EMF equation. So these are all the contents we can also cover in transformers, the principle of operation of single phase transformer, EMF equation, and we can also see how an ideal transformer and how it differs from a practical transformer, and we have to see how a phasor diagram has to be drawn for different loadings, and initially it has to be begin from no load, and then we have to see the equivalent circuit of a transformer and voltage regulation, and finally efficiency. Ultimately, efficiency plays a very vital role in any of the things. So the basic advantage of AC over DC is all about the role of transformer, because transformer plays a very vital role in transmitting the voltage levels from one level to higher level, and also vice versa, from higher voltage to lower level. And this is what we generally call as step up transformer and step down transformer. Even in our general power systems, this is how we say initially it will be starting from generation, and then it has to be transmitted, and then it has to be distributed. So we, the customers and all, will be coming under this third category, which is all about your distribution system. So this is where home appliances, initially it will be starting from generation, power transmission and transmission substation, and through poles distribution substation it is coming, and finally it is reaching to the residential consumers, where we all comes under that category. So this is a basic 132 kV by 33 kV 80 MVA transformer setup in one of the substation. So this is all about a step down transformer. So transformer is a static device which helps in transforming of electrical power in the circuit of which works on the same frequency, and it will transfers the voltage from one level to another level without changing in frequency and also the flux. So the applications of transformer, even in the previous slide we have seen the power transformers, distribution transformers, auto transformers, which are exclusively used in our educational sectors in experimenting auto transformers, and in substations we also see the instrument transformers. So this is how a transformer looks like, and this is how a distribution transformer looks like, and this is a single phase auto transformer, and this is a three-phase auto transformer, phase neutral, RYB with respect to neutral. So especially when we conduct load test on single phase transformer, there will be using this kind of single phase auto transformers. Auto transformer, because for example in our laboratory we will be using 115 by 230 volts transformer whose rating is 2 kVA transformer. So the supply what we are getting to this transformer is 230, and we are supposed to give it to its primary 115 volts. So there will be using this kind of single phase auto transformer, and this is said to be your three-phase auto transformer for regulating your voltage, especially in our machines laboratory while conducting brake test on three-phase induction motor. We use this three-phase auto transformer for regulating your voltage in order to maintain the main constant supply voltage, because induction motor will be running, initially running its rotor speed will be around 1498. When we are gradually applying the brake, voltage dip should not occur. So in order to regulate your voltage, three-phase auto transformer will be using in brake test of three-phase induction motor. So this is how an instrumental transformer looks like, and which is generally used in our substations. So this is your main transformer. This is how exactly it looks like. So when this is said to be your primary winding, which is generally denoted with N1, and this is said to be your secondary winding, which is denoted with the symbol N2, and this is the core of the transformer. The vertical is said to be the limbs of the transformer, and the bottom and top, the horizontal paths, are said to be the yoke of the system. and these n number of windings will be wounded over the primary part from which the electrical input is supposed to be given, and these n2 number of turns will be wounded on the secondary part of this core where the transformed voltage will be received at this end. In general, we can also call this is your sending end and this is your receiving end in generic, but as far as this electrical terminology is concerned, this is said to be your primary part and this is said to be your secondary part. So N1, N2. So initially when electrical input is given to the primary of our transformer, alternating current starts flowing through the primary part and then flux gets established, and that flux is also of your alternating flux. So this is your alternating flux which will be of sinusoidal shaping and which reaches its maximum part at the quarter of its cycle. So T is equal to reciprocal of your frequency. So at the quarter part, I am representing this with 1/4f frequency, and I am representing this maximum flux with the symbol phi m. When the primary winding is excited with alternating current at AC supply, so definitely it produces the alternating flux and current as shown below. So this alternating flux will be linking with both the primary and secondary, and this is the, we can also say this is the only quantity which is linking with both the primary and secondary. As the flux is alternating, definitely as per Faraday's laws, an EMF gets induced in the secondary. So this we call it as a mutually induced EMF. So this is how exactly the voltage from primary gets transferred to the secondary. So depending upon whether we want to step up or step down, it all depends upon the number of turns, and also that is what we are going to see in this equation. So here the terminology used for reducing the EMF equation of a transformer is all about the flux, where we are using the symbol flux, and the maximum flux that is reaching is time taken to reach its maximum flux is of quarter cycle. And let us consider N1 represents the number of turns in primary, and let us consider N2 represents the number of turns in secondary, and here E1, capital E1 represents the RMS value of the primary induced EMF, and E2 represents the RMS value of the secondary induced EMF, and the current that is flowing through primary is termed as primary current, which is all about the I1, and the current that is flowing through the secondary when the secondary is connected with its load is represented with the symbol I2. So from Faraday's laws of electromagnetic induction, the average EMF induced in each turn is proportional to the average rate of change of flux. So average EMF per turn is equal to your d phi by dt. And now d phi by dt is nothing about the rate of change of flux. So change in the flux divided by time required for change in that flux. That is all about the time taken to reach its maximum flux, which is we have seen in our slide phi m. So let us consider the 1/4 of the cycle of the flux, and completely cycle gets completed, and in 1/4 time period the flux reaches from 0 to phi, and thus there is a change in flux from phi m to initially it is starting from 0 and reaching its peak by phi m, and the time taken is of this. So average EMF induced per turn, we got it as 4 into f into phi m volts. So as we know that this flux is alternating and sinusoidal, the induced EMF in each turn of both the windings is also sinusoidal in nature, no doubt about that. And for sinusoidal quantity, we know the form factor of a pure sinusoidal is 1.11. So here we will be utilizing that form factor for getting your average value and also to determine the RMS value of the primary and also secondary induced EMF. So here we know that the form factor of a pure sinusoidal is 1.11, and for getting that we use the equation RMS value divided by average value. So average value is only known to you and the required part is only your RMS value. So RMS value is equal to 1.11 into average value. So therefore the RMS value of the induced EMF per turn, here right from the beginning we are trying to deduce per turn. So 1.11 into so deduce rate of change of flux d phi by dt, 4 into frequency into the maximum flux. So here we have considered N1 be the number of primary turns and N2 be your number of secondary turns. So thus EMF primary RMF equation of the primary induced EMF E is equal to 1.11 into this into your number of turns on primary. So finally we got E1 is equal to 4.44 your flux into frequency into N1 number of turns. And if the same, I can also use the same RMS value of induced EMF equation for getting the secondary induced EMF just by multiplying this equation with N2 number of turns in the secondary. So thus we got E2 is equal to 4.44 into flux into frequency into N2 number of turns. So these are all the two equations which will be used for calculating the RMS value of induced EMF for both primary and secondary turns. So if I consider this as my first equation and this as second equation, just second equation divided by first equation, I will be getting the voltage ratio. E2 by E1 is equal to N2 by N1, which is considered to be as the voltage transformation ratio K. Transformation ratio. If at all the value obtained K is greater than 1, if at all the values so obtained using these values is greater than 1, then the transformer is said to be step up transformer. Step up. And even from this also depending upon the number of turns, we're seeing this kind of representation of the turns of a transformer, we can also say this is a step-up transformer. If N2 is greater than 1, the number of turns on the secondary are more than number of turns on the primary. Even through indication also we can say this is said to be a step-up transformer. And definitely N2 by N1 or E2 by E1 we will be getting step-up greater than 1. And if at all the value of K is less than 1, if N1 is less than N2 or if E1 is less than E2, so definitely the value of K so obtained using this voltage transformation ratio will be less than 1, and in such case that type of transformers are said to be step down transformer. Step down transformer. So let us consider 33 kV by 11 kV. So this is a step down transformer. Step down transformer. Definitely it will be less than 1. And the third case is all about if the number of turns on primary gets matched with the number of turns on secondary. N1, N2 gets equal. In such case, the transformation value will be equal to 1. In such case, the K value will be equal to 1, and that type of transformers are said to be isolation transformers whose ratio is said to be 1:1. So here, depending upon the value of K, we can decide whether the transformer is a step-up transformer or step-down transformer or it is an isolation transformer. So here this 33 kV by 11 kV is said to be a step-down transformer, and 11 kV input when we give 11 kV, for example, if at all it is stepping up to 33 kV, this is said to be step-up transformer. So this is also a transformer, this is also a transformer. So a transformer is a static piece of device which has the capability to transform the voltage from one level to another level, whether it may be a step up or step down. So this is how exactly even in our Indian system, even 11 kV up to 765 kV we are using. 33 kV, 66 kV, 132 kV, 220 kV, 400 kV, and finally this thing. So everywhere the transformer will be stepping up, and in electrical representation 11 kV to 33 kV, 33 kV to 66 kV, 66 kV to 132 kV, 132 kV to 220 kV, 220 kV to 400 kV, 400 kV to 765 kV. The transformer is being stepped up at every intermittent points, and all this will be happening only in the substations. So here, let us consider how to calculate the full load value of primary and full load secondary current. Let us consider my transformer is of 115 by 230 volts, and let us consider 2 kVA. Its rating is of 2 kVA. So even if I don't have the values of number of turns, N1 and N2 were not known to me. N1 is not known to me, N2 is also not known to me. Only my primary voltage and secondary voltage. From this I have decided this is a step-up transformer. Only the thing I have is full load kVA is, kVA rating at full load is 2 kVA. So V1, I1 is equal to 2 kVA and V2, I2 is equal to 2 kVA. So V1 is your 115 volts, I1, so full load. And here I2 full load secondary current, secondary voltage is 230, 8.69 amps, 17.32 amps. So this is your full load primary current and this is your full load secondary current. During your experimentation, while conducting the experiment, when we are applying gradually the load on secondary of your transformer, initially, right from the beginning of your experiment, we have to observe the ammeters which were kept on primary and also the ammeters which were kept on your secondary, because we have to calculate initially the full load capacity of your primary current, which is all about your 17.32 amps, and the full load current of your secondary is 8.69 amps. So without exceeding these values, you can keep on increasing your load on your transformer, and thus we'll be calculating, depending upon the load, type of the load you are applying on your secondary, we'll be calculating the efficiency. So without observing this, we cannot, because these are said to be your full load primary current and full load secondary current. Let us solve some numerical problems. A single phase 50 Hz transformer has N1 80 turns on the primary winding and 400 turns on the secondary winding. The net cross-sectional area of the core is 200 cm square. If the primary winding is connected to 240 volts 50 Hz supply, you are asked to determine the EMF induced in the secondary winding and the maximum value of the flux density in the core. Right. So the EMF induced in the secondary winding, so we are asked to calculate E2 and also the maximum value of flux density. And we know flux density is all about your flux per unit area. So initially, let us write down your frequency is 50 Hz. N1 number of turns in the primary is 80 turns and N2 number of turns on the secondary is 400 turns, and the net cross-sectional of the area is given as 200 cm square. So we have to convert this into meter square. And your E1 is 240 volts. So what we are asked to deduce is all about your E2 and also your E1. So we have, when we have the values of N2 and N1, can't we calculate the value of transformation ratio? N2 by N1 is equal to 400 by 80, which is equal to 5. So we got the value of K. And also we have E2 by E1 is equal to your K. Can't we calculate the value of E2? E2 is equal to your K times of E1, which is equal to 100 volts. So we got the value of E2 as 1200 volts. So E1 is 240 volts and E2 is 1200 volts. So even by seeing this also, this is a step-up transformer. Even by seeing this voltage ratio also, we can say that this is a step-up transformer. And the second part, what we are supposed to calculate is the flux density, BM. So for getting this flux density, area of cross section is known and phi m is supposed to be calculated. And also from this recent deduced equation, we have E2 is equal to 4.44 into frequency into flux into your N2, your first equation, right? So can't we calculate the value of this thing? $50, and your N1 number of turns is equal to this thing. So finally we'll be getting 0.0135 vapors. The flux that is linking with both the primary and secondary turns is 0.0135 vapors. So area of cross section is known to you, so we can also calculate. Which will be getting as 0.675 Weber per meter square. This is how we can calculate the amount of EMF induced in the secondary winding and also the maximum value of the flux density depending upon the given data. So let us move on another type of the problem. So another problem which is also based on the same first type of problem which we have solved. A single phase 50 Hz transformer has N1 is equal to 120 turns, N2 is equal to 200 turns, and the net cross sectional area is also given, and your E1, the primary voltage is 270 volts and frequency is 50 Hz. Even in this problem also we are asked to calculate what is the amount of EMF induced in your secondary and what is the maximum value of the flux density in the core. So here N1 is known to you, N2 is known to you. Can't we calculate the value of K? And once K value is got, E2 by E1 is equal to K. So again using which we'll be getting E2 value as 450 volts. So again using the same thing, E2 is equal to 4.44 into frequency into flux into your N2. So flux will be calculating and we will get flux as 0.01 vapors. And again flux density is equal to flux per unit area, after which we will be getting 0.01 vapor per meter square. So the same kind of problem can also be solved using different thing. So by using direct expression also we can calculate, but for calculating that flux is not known to you. So that's the reason we went into this equation using the same voltage transformation ratio. So moving on to another type of problem, which is a single phase 50 Hz transformer whose rating is 250 kVA and it is definitely a step down transformer, 11 kV by 415 volts, has 80 turns on the secondary. So determine the approximate value of the primary and secondary currents. Second bit is the approximate number of turns of primary, and the third one is the maximum value of the flux. So maximum value of the flux and the approximate number of turns and approximate value of I1 and I2. No doubt these are your full load. So initial we'll be writing down the rating of the transformer is 250 kVA. This is a single phase transformer. Your E1 is 11 kV and E2 is 415 volts and it is having 80 turns on its secondary. So N2 is equal to 80 turns. We are asked to calculate I1 and I2, full load primary current and full load secondary current. So we can use V1, I1 full load is equal to your 250 kVA. I1 full load is equal to 250 divided by your 11 kV. So which will be getting around 22.727 amps. And full load secondary current we need to calculate. So even this we can calculate. V2 I2 is equal to your 250 kVA and I2 full load is equal to 415 volts, which will be getting around 602.40 amps. These are all said to be your full load primary current and full load secondary current. Even during experimentation also, by keeping these full load primary current and secondary current into consideration, the experiment has to be considered. So first we have completed how to determine our full load primary current and full load secondary current. Next is all about your number of turns. When N1 is known to you, can't we calculate the value of N1? Yes, we can. And here also we have the ratio E2 by E1. So K is equal to E2 by E1 is equal to N2 by N1. So N1 will be getting it as 2120.48 turns. So here we can round figure it as 2120 turns. Number of turns on the primary. And last, we are supposed to calculate the flux which is been linking with both primary and secondary. So here we have E1 and E2. Anything we can calculate. So let us go with the third expression. E2, which is equal to your 415 volts. We have the expression 4.44 into frequency into flux into your N2 number of turns. So flux is equal to 415 which will be getting around 0.023 amperes. This is how we can calculate, and this is how we can have various varieties of problems using this EMF equation of transformer. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.